The book talks about the consequence of the pigeonhole that states that the decimal representation of a rational number either terminates or repeats. They get into it a whole lot more than I do here in this video, so I highly recommend that you take a look at that and read the book if you haven't read the book yet. But basically, I'm gonna divide 3 and 14, and just like I did on this page, and I'm just gonna show you the idea of the theorem. Since I'm dividing by 14, by the way, according to the division remainder theorem, my remainders are either going to be 0, 1, 2, 3, or all the way up to 13. I cannot have any other remainders. And the idea behind this division is once your remainder starts repeating, that's basically it. It's pretty much, it means that the pattern is going to repeat forever. Okay, so I started by dividing 3 by 14, and then it doesn't work. 3 does not go into 14. So that's the reason why I put 0 point and I added the extra 0. So my first remainder, if you want, was basically 3. It did not work. So once you put the 0, then you can fit 14 into 30 twice. That's the reason why I have a 2. And then I start dividing. At every point in time, I kind of highlighted the remainder. The 2, the 6, the 4, and the 12, the 8, the 10, and the 2. So once I see the same remainder again, so in this case 2, that means if I continue, I'm going to be putting a 0 here, and 14 is going to go 20 twice. And so that means I'm going to now have the same list just repeating forever, okay? So that's kind of the idea behind what they're saying in the definition, that the decimal representation will either terminate or repeat. It cannot be always something brand new every single time, at least not for rational numbers. Okay. Again, that's because there are only 14 possible remainders, 0, 1, 2, 3, or, all the way up to 13. It cannot be anything else. So it has to pretty much repeat, or it has to terminate. Now, this basically tells me that numbers such as this or this are basically going to be automatically irrational numbers. So over here on the first number, for instance, the pattern is 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0, and so on and so forth. So yes, I can describe the pattern to you. There's always going to be an extra 1 every time. So I'm always putting an extra 1, and every time I separate it with a 0 from the next basically couple. But it's not repeating. It's always a different combination of ones. First, I had a single 1, then I have 2, then I have 3, then I have 4, and so on and so forth. So something like this is automatically going to be known as being an irrational number. If you take a look at the second one, it also has a similar kind of a pattern. I can build it very easily. I can describe the build, how you get it very quickly, but it's again not going to be a rational number. It's going to be irrational. So over here, what I'm doing is I'm writing 1, then I'm writing 1, 2, then 1, 2, 3, then 1, 2, 3, 4, and then so on and so forth, 5, 6, 7. So the last one is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, and then the next one is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so on and so forth. So I'm always adding an extra integer at the end of the list, and I just start over with my list. So it's predictable. You can kind of know what the next guy is going to be like. However, it's never going to repeat the same digits. It's always going to be an extra new digit that wasn't there previously. And so this is never going to terminate. So that means, again, that this number is not a rational number. It's automatically an irrational number. So that's kind of an application of the pigeonhole principle. So something that's so basic can lead us to rational and irrational numbers. So that's pretty cool.